In the previous class, we have seen introduction to time response analysis. Transfer function. Suppose I'm having a system. G of S. G of S is a system. The input to the system is R of t. Output of the system is C of t. The input to the system is R of t and the output of the system is C of t. If we take Laplace transform of C of t, you will get C of S. The same way, if we take Laplace transform of R of t, you will get R of S. The ratio between C of S and R of S is called transfer function. So, the model of the system is represented as ratio between the Laplace transform of output and input. Here you can notice that the denominator degree of the transfer function is n. It means the system is nth order system. Suppose I'm having a second order system, means its mathematical model will have second order differential equation d square y by dt square plus b dy by dt plus c y equal to x. Suppose if you find a transfer function for this, that is output y of s upon x of s, if you find its degree will be 2. You can notice that a s square y of s plus b s y of s plus c y of s equal to x of s. Therefore, the output upon input y of s upon x of s equal to 1 upon a s square plus b s plus c. So, this degree indicates that the system is second order. So, this is starts with the s power n. The degree is n. Therefore, nth order system. Always the numerator degree is less than denominator degree. Or n is always greater than m. N is always greater than m. All physically realizable systems, the denominator degree will be higher than numerator degree. N always greater than m. Then only it is physically realizable. Otherwise, it may not be physically realizable system. If a physical system is available, means definitely its mathematical model will have denominator degree will be higher than numerator degree. The transfer function can be represented in two ways. G of s can be represented in two ways. One is called time constant form. Another one is called pole zero form. Time constant form. Another one is called pole zero form. Suppose this is the polynomial, denominator polynomial of second order system. If you find the roots for this, how many roots you will get? 2 roots you will get. Let us call them as z1 and z2. This polynomial can be represented as s plus z1 and s equal to minus z1, s equal to minus z2. These are the 2 roots of this polynomial, z1 minus z1 and minus z2. Therefore, s plus z1 plus s plus z2. If you do this, what you will get? You will get the polynomial, because we are factorizing this polynomial by its roots. So this is, so if you factorize the denominator, you will get like this. So P1, P2, P3, etc., Pn or Z1, Z2, Z3, etc. Zm. Numerator roots are called Z1, Z2, etc. Zm. Denominator roots are called P1, P2, etc. Pn. If S equal to minus Z1, then you will get S plus Z1, S plus Z2 you will get. Here you are getting the roots are S equal to P1, P2, etc. Pn. Therefore, the denominator can be factorized like this. Similarly, numerator polynomial also can be factorized like this. S minus Z1 is Z2, etc. S minus Zm. This, if you factorize and write the transfer function like this, then it is called pole zero form, because P1, P2, etc. Pn are roots of denominator. Z1, Z2, Z3, etc. Zm are called roots of numerator. Roots of denominators are called poles. Roots of denominator polynomial are called poles. Roots of numerator polynomial are called zeros. Roots of numerator polynomials are called zeros. Therefore, we are writing in terms of poles and zeros. P1, P2, P3, etc. Pn are poles. Z1, Z2, Z3, etc. Zm are called zeros. If you write in this form, then it is called pole zero form. If you take this P1 out of this polynomial, out of this factor, what you will get? What you will get? Let us take a second order system. P1 S plus P2. Numerator, you are having a K and S plus Z1. This is second order system. Why second order? Two poles are there, that's why second order. Pole zero form. If you take P1 outside, what you will get is K Z1 1 by Z1 S plus 1 whole divided by 1 by P1 S plus P1, sorry, S plus 1 1 by P2 S plus 1. This is 1. So outside you will get P1, P2. Therefore, what are the constants? Now K dash equal to K times Z1 upon P1, P2. That is K dash. Now the K becomes K dash equal to, here you are taking Z1 outside. Here you are taking P1 as well as P2 outside. That's why this becomes like this. Therefore, K dash equal to K Z1 upon P1, P2, or we can say that K dash T Z1 S plus 1 upon T P1 S plus 1 multiplied by T P2 S plus 1. So this 1 by Z1 equal to T Z1. 1 by P1 is equal to T P1. 1 by P2 is called T P2. That's all. This TP1, TP2 are called time constant of the system. TP1, TP2 are called time constant of the system. These are all called time constant. That's why this TP1, TP2, TPN are called time constant of the system. That's why this form is called time constant form. Time constant form. So we can represent the transfer function in two ways. One is called a time constant form. That is, S will have coefficient. S will have coefficient plus 1. Pole zero form means S do not have any coefficient. S plus P1, S plus P2, etc. Like that it will be represented. S plane. Already you know what is S-plane. S-plane is a complex plane. S-plane is a complex plane. Complex plane. What is complex plane? The horizontal axis will be sigma. Vertical axis will be j omega. That is called complex plane or S-plane. Simply called S-plane. If you plot the poles, of these systems, plot how to plot here S plus P1. How you find the roots? S equal to minus P1. S equal to minus P2. For that second order example system, the roots are roots of the denominator are minus P1 and minus P2. Or say minus 2, minus 3. Minus 2, minus 3. If you plot in this S-plane, minus 2 will be here, minus 3 will be here. So these are all poles of the system. Numerator roots are called zeros. S equal to minus Z1. That is equal to, say, plus 2. Then where it is, it will be mentioned here. It will be mentioned here. This is 0. 0 will be represented by a circle. Poles will be represented by X mark. Poles will be represented by cross mark or X mark. And zeros will be represented by a circle. So here, the poles are in the left hand side, left half plane. This is the right half plane. So there is a significance of location of these poles and zeros that we will see later. But how to plot them like this? The complex plane, you can plot like this. Suppose the poles are S equal to minus P1. Another pole is called minus P2. S equal to minus 2 plus J1. Another pole is minus 3 plus J2. You can plot this. Then plus or minus, minus 2 minus J1. So it must be in complex conjugate only. You cannot write otherwise. So minus 2 plus J1. This pole will be here. This is P1. Minus J. This will be here. P2. So it may be a complex roots also, complex poles also. Here the P1, P2 are called complex poles. Here the poles are real poles. Only real part alone is there. That's why it is called real poles. Similarly, zeros can be a complex or real. That's why you need a complex plane to represent them. S-plane or complex plane. The location of these poles are very important. It has significance that we will see later. Already I told you that the order of the system means the order of the differential equation. These two are first order systems. This electrical system is first order system. Because if you write the differential equation for that, it will be a first order differential equation. Let the output be V naught of t, voltage across the capacitor. Input be Vi of t. If you write the differential equation for this Kirchhoff's voltage law, we have to write. The applied voltage is Vi of t equal to, let us assume that current through this circuit is I of t. Therefore, Vi of t equal to Ri plus 1 by C integral of I dt. That's all. Or I can, if I take Laplace transform of this, what you will get? V I of S equal to R I of S plus, assuming zero initial conditions, 1 upon CS I of S you will get. Let it be 1. Let it be 1. What is the output? V naught of S. V naught of T. V naught of T is the output. That is equal to 1 by C integral of I of T dt. I of T dt. If we take Laplace transform, 1 by CS I of S. From this you can find I of S. I of S equal to CS V naught of S. CS V naught of S. So let it be second equation. Substitute the value of I of S from the second equation, first equation. What you will get is V I of S equal to V I of S equal to V I of S equal to R plus 1 upon CS multiplied by I of S equal to CS V naught of S. If we simplify this, what we will get? RCS plus CS getting cancelled. Therefore, RCS plus 1 multiplied by V naught of S. What is output? Output is V naught of S. What is input? VI of S. Therefore, the transfer function is output by input. That is V naught of S upon VI of S equal to 1 upon RCS plus 1. RCS plus 1. What is the order of this differential equation? It is not differential equation. It is integral equation. If we differentiate this once, what you will get? dVi of t by dt or di by dt plus 1 by c I of t. That's all. So it is first order differential equation. First order differential equation. First order differential equation. Therefore, here the degree of S is 1. The degree of S is 1. Therefore, this equation, this system is first order system. First order system. This is also first order system. This is also first order system. What is this system? This is a level system. There is a outflow rate Q naught. There is an inflow rate QI, like your overhead tank, your home. QI, Q naught, QI is outflow rate, QI is inflow rate, liters per hour, liters per minute, like that. Or kg per minute or kg per second, like that. This H is the output. I want to maintain this level H, irrespective of outflow rate. So what I have to do to maintain the level? I have to adjust the inflow rate equal to outflow rate. If you maintain inflow rate equal to outflow rate, level remains constant. So what we have to do? We have to measure the height. If any change in height, if the height decreases, we have to increase inflow rate. If height increases, we have to decrease inflow rate. That's all. That is the idea of control. So like how we are controlling the speed of the car, we are seeing the speedometer. If speed increases, we'll decrease the input. If speed decreases, we'll increase the input. Like that, if level decreases, we'll increase the input. If level increases, we'll decrease the input. That way we can control the level. If you find the mathematical model of this, dH by dt equal to dH by A, dH by dt. A is area of cross section of the tank equal to Qn minus Q naught. This is also first order system. This is also first order system. So this will be represented by output by input. H of S upon input is Qi of S, inflow rate, equal to 1 upon tau S plus 1, K by tau S plus 1. K by tau S plus 1. We do not know the value of K and tau. We do not know the value of K and tau, but anyhow, it is a first order system. So I can simply write K upon tau S plus 1. K upon tau S plus 1 I can write. So this is a first order system. That's why we can represent them K upon tau S plus 1. So first order system means if it is in differential equation, it will be represented like this. Tau dh by dt plus h equal to k q I q in of t. The same is represented in differential equation. If you find the mathematical model of this tank, you will get like this. You will get like this. You will get like this. Now, we know the mathematical model. We know the mathematical model in two forms. One is in differential equation form. Another one is transfer function form. Transfer function is from differential equation. Another form of differential equation is transfer function by assuming zero initial conditions. Another form of differential equation is transfer function. By using the transfer function, if you give any input, we can find the output. We can find the time response. What is time response? For a given input, if you draw the output of the system with respect to time, then it is called time response. We can draw the time response for a given system if we know the transfer function of the system. Suppose I know the transfer function of a first order system. Hereafter, I will say first order system. You can assume that it may be a RC circuit, or it may be a level tank, or it may be something. Yeah, some first order system you can assume. A thermometer, you can assume it as a thermometer, first order system. Like that, you can assume. But hereafter, we won't say this is the system, that is the system. We won't say first order system, second order system, third order system, like that we will say. I am taking a first order system whose transfer function is k upon tau s plus 1. K upon tau s plus 1. Its time constant is tau, its gain is k. I'll tell what is k, what is tau, what is time constant, what is gain, I will tell later. K upon tau s plus 1, this is first order system. Or I can write G of s can be written as C of s upon R of s, C of s upon R of s upon K upon tau s plus 1. That way I can write C of s upon R of s equal to K upon tau s plus 1. Tau s plus 1. We can write like this. Suppose I want the response if R of s is an impulse function. R of s is an impulse function. If R of s is an impulse function, then what is the response? Response means output. Response means output. What is the output I want to find? So impulse function, already we know that R of s and R of t, we know the relation. R of t impulse function, del of t, unit impulse function. For that, the Laplace transform of del of t is 1. R of t is u of t, unit step function, u of t. Then its Laplace transform is 1 upon s. If it is a ramp function, R of t, ramp function, then it's Laplace transform 1 upon s square. If it is parabolic function, then it's the Laplace transform 1 upon s cube. Here it is, let us assume that it is an impulse function. Input is an impulse function. Therefore, R of s equal to 1. 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 How to find the response of the system? What is in the left hand side? C of s. If you take Laplace inverse, you will get C of t. Similarly, in the right hand side also, you have to take the Laplace inverse. If you find a Laplace inverse of this, you will get automatically output. So R of t is R of s is 1 and substituted. I have to take Laplace inverse. To find the Laplace inverse, I have to write in this form, s plus whole zero form. To find the Laplace inverse, I have to write in whole zero form. That's why I'm taking tau outside. Therefore, tau multiplied by s plus 1 by tau. 1 becomes 1 by tau. If I take tau outside, therefore, this can be written as k upon tau whole divided by s plus 1 by tau. If we take Laplace inverse of this, what you will get is, if you take Laplace inverse, what you will get is k by tau is constant. 1 upon s plus a. What is Laplace inverse of 1 upon s plus a? E power minus at. E power minus at you will get. So here, instead of a, it is 1 by tau is there. Therefore, e power minus t by tau you will get. T by tau you will get. So this is the C of t. This is C of t. The time response, impulse response of the system. C of t equal to k upon tau e power minus t by tau. K upon tau multiplied by e power t by tau is the time response in mathematics. We have to plot the response. How we can plot the response? We have to vary the t from 0 to infinity. We have to vary t from 0 to infinity and find various values of C of t. Then we can plot. Here it is plotted. X-axis is time axis from 0 to infinity. Y-axis is magnitude. When t equal to 0, what you will get? E power minus t by tau. When t equal to 0, e power 0 is 1, you will get k by tau. When t equal to 0, the magnitude is k upon tau. The magnitude is k upon tau. If you give impulse input, the magnitude becomes k by tau. If you substitute t equal to infinity, what is the final value? If t equal to infinity, e power minus infinity equal to 0. E power minus infinity equal to 0. Therefore, the final value is 0. Therefore, it starts from k by 2. Finally, it ends at 0. Exponentially decreases. This is the response. Time response of first order system for impulse input. This is the time response. This is the time response of the system. What is the waveform of this response? K by tau e power minus t by tau. That is the waveform. K by tau e power minus t by tau is the waveform. This is the time response for impulse input. Time response for impulse input. Time response for impulse input. The same first order function, but that step input. R of t equal to u of t. U of s equal to 1 upon s. Therefore, C of s upon R of s, that is transfer function, equal to k upon first order system, tau s plus 1. If you substitute R of s equal to 1 by s, what you will get? C of s equal to 1 upon s multiplied by tau s plus 1. K upon s multiplied by tau s plus 1. You will get. Now we have to find Laplace inverse that we do not know. So we have to factorize this. We know Laplace inverse for each factor. That's why let us factorize. That is equal to a upon s plus b upon tau s plus 1. B upon tau s plus 1. A equal to what? A equal to s multiplied by k upon s multiplied by tau s plus 1 at s equal to 0. If you substitute s equal to 0, a equal to k. Therefore, similarly, we have to find b also. B equal to tau s plus 1, k upon s multiplied by tau s plus 1, where s equal to minus 1 by tau. S equal to minus 1 by tau. Because tau s plus 1 equal to 0 means s equal to minus 1 by tau. If you substitute These two are getting cancelled. These two are getting cancelled. S equal to minus 1 by tau. If you substitute, you will get minus k. Here, S equal to 1 minus 1 by tau. If you substitute k tau, you will get. K tau, you will get. So we got A and B values. We got A and B values. A equal to what? K. K upon S plus B equal to minus KT. KT upon K tau upon tau S plus 1. Now we can find the Laplace inverse. K upon S minus. To find the Laplace inverse, we have to write in pole zero form. Therefore, if you take that t outside, you will get S plus 1 by tau. Or you can write k multiplied by 1 upon S minus 1 upon S plus 1 by tau. Now we factorized. C of S equal to C of S equal to k multiplied by 1 upon S minus 1 by S plus 1 by tau. If you find the Laplace inverse, you will get C of t. C of t equal to 1 upon S. It is step. That's why one unit step. 1 minus k multiplied by 1 minus. K is outside. K is outside. Therefore, k multiplied by 1 upon S is 1. Laplace inverse. If you take Laplace inverse for this, you will get e power minus t by tau. Therefore, this is the step response of the first order system. Step response of the first order system. C of t equal to k multiplied by 1 minus e power minus t by tau. To plot this, we have to vary t from 0 to infinity. To plot this, we have to vary t from 0 to infinity. If you substitute t equal to 0, C of 0 equal to what? K multiplied by 1 minus e power 0 equal to 1. That is equal to 0. So it starts at 0. Impulse response where it starts? Starts at k by tau. Impulse response starts at k by tau. Impulse response starts at k by tau. Here, if you see that here, step response starts at 0. C of infinity equal to what? Final value. Final value equal to what? Final value equal to, we have to substitute t equal to infinity. E power minus infinity equal to 0. Therefore, the final value is k. Final value is k. Therefore, finally, it will settle at k. Initially, it will be at 0. Initially, it will be at 0. Therefore, the response is step response is C of t. Starts at 0, end at k. End at k. So the response will be looking like this. Up to infinity, it remains at k. Final value is k. It remains at k. It remains at k. Here, we can find the definition for time constant. We can find the definition for time constant. The definition for time constant, tau, we have seen, in the transfer function tau. The transfer function tau, the definition for this tau is, time taken for step response. Time taken for the step response to reach 63.2% of final value. 63.2% of final value. This is 100%. This is 100%. 100% is what? K. K is the 100%. Finally, where it reaches? At kth value, it reaches. At kth value, it reaches finally. But initially, it is 0. Gradually, it increases. Finally, it reaches k value. While reaching, sometime it will be at 63.2% of final value. 63.2% of final value. At the time taken to reach this point, is called time constant tau of this system. This is called tau. The time taken, say 5 seconds means the transfer function can be written as k upon tau 5s plus 1. I can write k upon 5s plus 1 because tau equal to 5. How I got tau value? Time taken to reach 63.2% of final value for a step input. That is very important. We have to mention the step. Time taken to reach 63.2% of final value for step input. For step input, time taken to reach 63.2% of final value is time constant. If you know that is equal to 5 seconds, then the transfer function can be written as k upon 5s plus 1. So for different system, the time constant will be different. What is the definition for time constant? Time taken for the step response of a system to reach 63.2% of final value is known as time constant of the system. Time constant of the system. Time taken for the step response of the system to reach 63.2% of final value. So in this, for this system, it is 5 seconds. For this system, it is 5 seconds. For this system, it is 5 seconds. 5 seconds. Some other system, it may quickly raises to final value. For that system, the time taken is 3 seconds, 2 seconds. Some other system, further quickly it reaches final value. It is 0.5. 0.5. It takes only 0.5 seconds to reach 63.2% of final value. The first system takes only 0.5 seconds to reach 63.2% of final value. Second system takes 2 seconds to reach 63.2% of final value. Third system takes 5 seconds to reach 63.2% of final value. Which is faster? The first system, which takes only 5.5 seconds to reach 63.2% of final value. Therefore, the time constant, this system is fast system. Then this system, this is slow system. This is slowest system. This is slower system. This is fast system. Because the time constant is 0.5. For this time constant is 2. For this time constant is 5. As time constant increases, the system becomes slow. System becomes slow. By looking at the transfer function of first order system, we can say that how the system behaves. If time constant is large, means it takes long time to settle. Takes long time to settle. If time constant is very small, means it quickly settles. Fast system. It quickly settles. Fast system. So, what is C of t? We derived C of t equal to k multiplied by 1 minus e power minus t by tau. Am I correct or not? This is the response we got. This is the response we got. If you substitute t equal to tau, that is time constant tau. If you substitute t equal to tau, what you will get? K multiplied by 1 minus e power minus 1. Am I correct or not? 1 minus e power minus 1 equal to 0.632. 1 minus e power minus 1 equal to, this part is equal to 0.632. It means what? The time, from this we got the definition. That is 0.632 times is, you will get C of tau, you will get. When t equal to tau, you will get the output is equal to 0.632 times k. K is the final value. K is the final value. If you change k, what will happen? If k equal to 5, in this case, for all the system, I am having 3 systems. One is, this is third system, k upon 5s plus 1. Second system, k upon 2s plus 1. Third system, k upon 0.5s plus 1. Sorry. The first system is k upon 0.5 s plus 1, which is fast system. This is the fastest system because time constant is 0.5. Slowest system, this is because time constant is 5 seconds. Slower system, this is 2s. By looking at time constant, we can say that this is fastest. But in all the three cases, k equal to 5. That's why all settled at 5. K equal to 5. K equal to 5. That's why all settled at 5. Finally, it reaches 5 because k equal to 5. The k is called static gain of the system. K is called static gain of the system. K is called static gain of the system. Or simply gain. We can call it as simply gain. But it should be in time constant form. It should not be in pole zero form. The k is correct when it is in time constant form. That we can understand from here. Here, what I said, while writing pole zero form, I wrote k dash. While writing pole zero form, while writing pole zero form, it is written as k dash. While writing in time constant form, it is written as k. K is not equal to k dash because k dash equal to what? K dash equal to k multiplied by z1 upon tau 1, tau 2 for second order system. K is multiplied by z1 divided by tau 1, tau 2. That is equal to k dash. Therefore, k is not equal to k dash. If pole zero form means k is not correct. Time constant form is k is correct. Time constant form is time constant form means k is correct value of k. You will get correct value of static gain. You will get correct value of static gain. You will get. You understand this point? So this k means this k is in time constant form. Time constant form. It means what? It means what? The final value will be at k. The final value will be at k. If instead of 5, suppose I'm here, I'm having 5. Here I'm having 3. Here I'm having 10 means the first response will settle at 10. Second response will settle at 3. The third response will settle at 5. Here all k values are equal. That's why all settled at 5. I think now you understand the difference between static gain and time constant. Static gain and time constant.